I learn it as I write, and the actual writing is strong reinforcement in my own brain, because it's visual. I'm writing it out, so I get the sort of mechanical memory of writing it out. So that seems to help the memorization process. So by the time I've written it out, I've sort of 3/4 know it anyway, and then I read it over. I read it over before I read it over a couple of times. So just think, have I got it? Have I understood it at all? And so it's fresh in my short-term memory, and then I film, and then 5 minutes later, no, I'm kidding. Okay, so well, that's the preliminary remarks. Now the Turing machine. Let's get to the nitty-gritty. Okay, so at the end of the previous session, we were talking about the formal definition of the Turing machine. It was a 7-tuple, you may remember. These are the 7 things. Big Q, the set of states. Turing machine is similar to a finite state machine. It too has a finite number of states. Okay, so in fact these 3 sets here are all finite sets. The capital sigma, as usual, is just a set of input string symbols. The symbols allowed in your input string. But this is now, you could call it the string on your tape, right? Because it's a Turing machine, we're talking about tapes. And the capital gamma, what's that? That's the tape alphabet. That's the set of symbols allowed on your tape. So this is a subset of that, but this one can also include the blank symbol, because most took an infinite number of blank squares. So what does most mean? Infinity is an interesting question. That's where Cantor's work was so controversial. A lot of mathematicians hated Cantor. Right. So capital gamma is the tape alphabet. Symbols allowed on the tape, which includes all these and the blank symbol. And the blank symbol sort of, well, it looks like this. That's the blank symbol. Okay. Transition functions. You're mapping an ordered pair into an ordered triple. We talked about that at length. The start state Q0, the accept state Q accept, and the reject state Q reject. These two have to be different, and there's only one of each. There's only one accept state and one reject state, at least in this version of the relatively simple Turing machine that Sipser's talking about. Alright, so that's the formal definition. Now the guts of it, of course, is always the transition function, your delta, and that's where things with a Turing machine get really tedious, right? There's so many details and so many transition rules. So in practice, you tend not to give the full description, the formal description of the Turing machine. You only give a sort of relatively higher level description that's sufficient for you to understand how it works without every nitty-gritty detail. Right? For that, you need a transition table. Or a transition diagram, a state diagram. Okay, so that's the formal description. Now, how does a Turing machine compute? So we're talking more formally about how it actually computes. What is it? How does it do? Okay, so initially, your machine, the Turing machine, just call it M for machine, right? It's given an input, like an input string. Let's say of little n characters. Right? So you just have a contiguous string. Contiguous means no gaps, no hole, no blanks. Okay, each character is surrounded by, at least on one side, by other non-blank characters, symbols. Okay, so let's say you have n of them, and this contiguous string, if you like, call it W. It'll belong to sigma star, right? Just arbitrarily long strings where each element belongs to this. Okay? So sigma star, right? So that here is your input string. It's on the tape. Now Sipser, I'm not quite sure why he did it, but it seemed to be simpler just to have the tape infinite, extending infinitely in both directions. But he has a tape that where there's a boundary on the left-hand side of the tape, and it extends infinitely to the right. Your right this way, but here on the left is like the first square on the tape. I don't know, I chose to do it that way. Okay, so this string here will start on the left-hand side. So this first symbol here will occupy the first square on the tape, right? And this one will occupy the second square on the tape, and so on. This one will occupy the nth square on the tape. And then after that, all the squares after that on this infinite tape extending to the right, they're all blanks. You can, in a sense, you could say they all contain this blank symbol. Now I don't know how to say that. I've never come across a word. It sort of looks like a cup, but I just call it a blank symbol. If you know what the word is, if you know what that symbol is called, if it has its own word, its own label, I'd like to know what it is, because I've never come across it. All right. Okay, so the rest of the tape is blank, except for this. This is on the left-hand side of the tape, and all the rest of these blanks, blank symbols, look like a cup. Okay. Now, if you start here and imagine you're reading across, and you imagine the head, the read-write head of your machine, your Turing machine, is here. So that's the current position. And then you read one more square to the right, you'll get a blank. And when that happens, you know that that blank, that means that you have reached the end, well, in fact, one square beyond, the end of the input string. Okay? So you W1, W2, Wn, blank. Okay? So you know that symbol there was the last symbol in your string, input string, okay, on your tape. What else? Okay, I was just saying here. All right. So how does it work? Like, how does it actually compute? Well, typically, so you put this string on the very left-hand end of your tape. Now remember, Sipser's starting version, if you like, of the Turing machine has a boundary. It has a first square on the tape, and there's just no tape to the left of it. Okay, there's nothing there. It's not even blank squares. There's nothing. So the tape starts at square one and goes infinitely that way. So like I was saying, you put these n symbols in the first n squares, and after that, infinitely, all the squares to the right, they contain blanks. Okay. So now you will start the computation by having the read-write head of the machine positioned at the first square. So it can read W1, the first symbol. Okay. And what it does then is it uses the rules from the transition function to go through steps, Turing machine step. So typically, it'll start in a start state. That's given. That's part of the formal specification. It'll start in Q0. Right? That's your start state. So your very first step of your machine, the first step in the computation by Turing machine, it'll start in this state, Q0. It will look at the first symbol in the string. In this case, it would be W1. And then it consults its transition table, in a sense. It goes to, within its control, is the transition function. So it inputs Q0, W1, right? In other words, current state and the symbol on the tape under the read-write head. In this case it's W1. And then the transition table will output the corresponding right-hand side of the transition rule, whose left-hand side matches Q0 W1. Right? So you get this output that's a triple, and the triple will be, it's a bit of revision from last board. It'll be the next state. That's the first of the triple. The second one is the symbol to be written on the current square, being read. So this here will get overwritten, and the W1 will disappear, and it will be replaced by this second thing in the triple. And the third thing, the head will move one square to the left or the right. Okay, and so that will then probably change. Well, the state will change probably. The contents of the tape, because you've overwritten, you've written something on the tape, so the contents of the tape will change, and the position of the head read-write head will change because it's moved left or right. Okay, so then you'll have a new state and a new symbol that's being read on the tape, corresponding to the position where the head read-write head is. Okay. And then you just go through this process again and again, just by using the rules, transition rules, in the transition function. So you input the ordered pair, your current state, current symbol being read, and you output the triple next state, symbol to be written at the current position, and the instruction to move left or right, L or R. Right? And you just keep doing this until, now you could go infinitely. Turing machines are quite capable, they'll just go on forever, unless, so how do you stop? Okay. Before I do that, there is a little complication, and this is why I'm a bit puzzled by Sipser. Right? Authors of textbooks are people, right? And people make judgments, and Sipser has made the judgment. It was a judgment call, as the Americans say, meaning a decision, that he would start his explanation of a Turing machine by having